All right, so we're going to continue talking about parallel lines. Um, and last time we talked about what happens when we had two lines, a transversal, and the two lines that are being cut by the transversal when they're parallel. There are some angle pair relationships that are developed, and if the two lines that are being cut by the transversal are parallel, then those relationships can either be congruent or supplementary. This time around, and here are the standards we're going to hit, but this time around we're going to figure out how to prove when those two lines that are being cut by a transversal are going to be parallel. And then we're going to get into a little bit of Algebra 1 review as far as if all of these lines are sitting in the coordinate plane, how to tell if, how to use slopes to tell if lines are parallel or perpendicular and that kind of thing. So, all right. Well, first things first, we need to remember what a converse is, right? And so you have to remember that to create a converse to an if-then statement, you're just going to switch the hypothesis and the conclusion, right? And remember that the hypothesis is what we need to know to be true. And if the hypothesis is true, then we can conclude the conclusion, right? We can conclude the then part. For example, we can write a conditional statement that says that if you are a clown, then you are funny. That means that if I know that someone is a clown, then I can conclude that they're funny. Now, if we wrote the converse for that, it would sound like if you are funny, then you are a clown. Which means now, if I know that someone is funny, then I can conclude that they are a clown, as long as it's a true if-then statement, right? So those are two different statements. One where we know someone's a clown, we conclude they're funny. The other one says, if I know someone is funny, then I can conclude that they're a clown, right? And if-then statements may be true, may be false, but that's how they work, okay? So we'll revisit that in just a second. Let's talk about this diagram here. My question for you is, can you determine or can you tell if line S and line R are parallel? And before you even try to say it, no, you can't say they just look like it. Okay? From the information in the diagram, can you conclude that those two lines are parallel? If you can, how could you do it with the information in this diagram? Right? Well, what kind of angles are angle 1 and angle 2? Yeah, the corresponding angles, right? And right now, the diagram tells us that those corresponding angles are congruent. The only way that's going to happen is if line S and line R are parallel, right? They don't have to be. Line S and line R do not have to be parallel in order to make these corresponding angles. Okay? The corresponding angles would still exist if S and R were not parallel. But when they are parallel, we know that those angles are congruent. So what we're looking at now is we already know the angles are congruent. So therefore, we can conclude the lines are parallel. Okay? Remember from the corresponding angles postulate, right? Postulate 15 from 3.2, which says, its if-then statement said, if two parallel lines are cut by a transversal, then the pairs of corresponding angles are congruent, right? Now, that's an if-then statement, and it's a true if-then statement. What if we wrote the converse? What would the converse sound like if we wrote it? Can you picture it? The converse, we just switch the if-then, and we say that if two lines are cut by a transversal, so the corresponding angles are congruent, right? And we can kind of leave this part out, right? And just say that if the corresponding angles are congruent, then the lines are parallel. Now these two statements, right here and right here, say two very different things. Just like the clown and being funny, if then and converse did, right? In the first one, in the actual postulate, that if-then statement says that if I know that there are two parallel lines with a transversal, then I can conclude that the corresponding angles are congruent. That is not what the converse says. The converse says that if I know the corresponding angles are congruent, so if I see a set of lines in a transversal and the corresponding angles are congruent, then I'll know the lines are parallel. Those two statements are different, and they're different in what you know and what you get to conclude. The original postulate tells us that we'd have to know the lines are parallel first. And if we did, then we could conclude that the corresponding angles are congruent. The converse says that we would have to know the corresponding angles are congruent first. That if they are, then we could conclude that the lines are parallel. That's how we prove that two lines are parallel. And that's with these angle relationships that we talked about in the last section. Okay? Now, what if we moved angle 1 to right here? Would we know that those two lines S and R are parallel? Well, hopefully you're looking at that and saying, well, those are alternate interior angles. They're congruent, and the only way that happens is that those two lines are parallel. So yeah, we'd be able to tell then. What if, instead of angle 1 being there, or if instead of angle 2 being there, angle 2 is here? Again, I hope you're saying to yourself, well, those are alternate exterior angles. And if they're congruent, the only way that happens is that those two lines are parallel. So then we would be able to tell those two lines, S and R, are parallel, right? What if angle 1 moved to here? Would we be able to tell then? Hopefully you're saying no. Those are consecutive interior angles. Consecutive interior angles would be supplementary if those two lines are parallel. Just being congruent does not mean they have to be supplementary. They might be, but they don't have to be, right? So that gets us into our converses of our corresponding angles, alternate interior, alternate exterior, and consecutive interior angles, right? So the first one was the corresponding angle postulate, which says, again, the postulate itself, just the straight up postulate says that the lines have to be parallel first, and then we say the angles are congruent. The converse flips it and says we'd have to know the angles are congruent first, and then we can say the lines are parallel. So it's all about order here. Okay? It's the converses that are going to help us prove two lines are parallel. Okay? So one of the ways we can use this converse of the corresponding angles postulate, right? So we've got this diagram here, and we want to figure out what value of x would make line M and N parallel. Well, what would have to be true about those two angles if line M and N were parallel? Now, they're corresponding angles, so they would have to be congruent. So that means 3x plus 5 would have to equal 65. And of course, through some simple algebra here, we can determine that x would have to be 20. So if x were any other value besides 20, then those two lines M and N would not be parallel. All right? Now, like I said before, the same thing is true for the other angle relationships, right? There was the alternate interior angles theorem that said if the two lines were parallel, right, then the alternate interior angles were congruent. Now we have the converse, which is also true. Okay, if the alternate interior angles are congruent, then we can conclude that the lines are parallel. And so another way we can prove two lines parallel. Same thing with alternate exterior angles, right? The original theorem said that if we knew the parallel lines first, then congruent alternate exterior angles. The converse says congruent alternate exterior angles first, then the lines are parallel. Okay? It's all about what you want to prove, what you want to conclude. Do you want to conclude that these angles are congruent? If you do, then you would have to know the lines are parallel first. If you want to prove that two lines are parallel, then you would have to show or know that the angles are congruent, at least the ones we've talked about so far. What about consecutive interior angles? They have to be congruent also, right? Wrong. Okay? Consecutive interior angles would have to be supplementary. The original theorem says that if the lines are parallel, if we know parallel lines first, then we know the consecutive interior angles are supplementary. The converse says the other way. If we know that the consecutive interior angles are supplementary, then we can conclude the lines are parallel. Okay? All right, so putting this to use. Here is the pattern on the snake skin of a diamondback snake. Okay, so the question is, the sides of the pattern, are they parallel? Can you tell? Well, I'm not sure in your notes if you can tell very well. And you might not be able to tell a whole lot better in this picture up here. But we're supposed to know that these angles are congruent. Now, here's one side of that pattern, and here's the other one, right, extended with these two lines. And then here's our transversal, right? So, in order for us to know that the sides of that pattern are parallel, we would talk about, well, the alternate interior angles are congruent, right? So, the lines that represent those sides are parallel. Therefore, the sides of that pattern must be parallel also. Okay? That's by the alternate interior angles converse. Right? So if you wanted to use that, let's say, in a proof, we would call this the alternate interior angles converse. And that's what leads us to know that the sides of that pattern are parallel. Okay? Some more questions. Is there enough information to conclude that line M and N are parallel? Okay? In this first diagram, we've got this angle is 75 and this one's 105. So just like in any other situation where you've got two lines in a transversal, the first thing you want to do is determine what angle relationship you might be dealing with, right? So what angle pair are these two guys, the 75 and the 105? No, they're not corresponding. They're not alternate exterior. There actually isn't a relationship. We briefly have mentioned same side exterior angles, but not anything that we're going to really use a whole lot in this class. So not any of the relationships that we've dealt with so far. So what do? Well, a couple of options here. I know that if I look at this angle here and this angle here, those guys are a linear pair. They form this straight line, right? They trace out a T, however you want to think of it. But those guys are a linear pair, and yet remember that linear pairs are supplementary. So if I subtract 75 from 180, I get 105 degrees. So that means that this angle here is 105. Now I've got this angle congruent to that angle. And if I go through and trace again, we get an F, which means that these are corresponding angles. So yes, there's enough information here because our corresponding angles postulate converse, or just corresponding angles converse, gives us the information we need. These two lines are parallel. How about over here? Angle 1 and angle 2 apparently are supplementary. They add to 180. Can you prove the lines A and B are parallel then? No, you definitely cannot. These are alternate interior angles and would need to be congruent. Just because they add to 180 doesn't mean that they're congruent. They can be, but they don't have to be. So we don't have enough information right now. We would need to know that angle 1 and angle 2 are congruent in order to prove that these lines are parallel. So this is a big fat no. Okay? So we're just trying to make sure we apply the theorems and postulates the way that we need to in the converses. Okay? All right. Here's a proof for you. prove that if two lines are cut by a transversal so that the alternate interior angles are congruent, then the lines are parallel. Basically, we're going to prove the alternate interior angle converse without using the alternate interior angle converse. You can't prove something with it, right? So here we go. We got this diagram. Angle 4, angle 5 are congruent because that was given to us. Okay. Next statement is angle 1 and angle 4 are congruent. Angle 1 and angle 4 right here. Why would they be congruent? Yeah, they're vertical angles. So by the vertical angles congruent, or the vertical angles theorem, we know that those two angles are congruent. Now, 1 and 5 are congruent. How do we know that? Well, actually, we can use these two statements here. We can't use the fact that 1 and 5 are corresponding angles. Why can't we do that? Because we don't know that G and H are parallel yet. We don't know that the corresponding angles are congruent. So 1 and 5 are congruent. That is true. But it's not because they're corresponding angles. And that's because we don't know the lines are parallel. Instead, we use the two previous statements and realize that with angle 4 being here, 1 and 5 are both congruent to angle 4, then by transitive or by substitution, we know that 1 and 5 are congruent. Now we know that 1 and 5 are congruent. And yes, we've already talked about 1 and 5 are corresponding angles. So if 1 and 5 are congruent, which we've just proven, the corresponding angles are congruent, then we know the lines are parallel. And that's by that corresponding angles converse. So we've managed to prove the alternate interior angle converse without actually using the alternate interior angle converse, which is what we want to do. Now, going forward from this day on, since we've proven that theorem, that converse, if we know that angle 4 and 5 are congruent, we can jump right down and say that the two lines are parallel because the alternate interior angle converse. That's the point in proving a theorem. Now we get to use the theorem. Okay? All right, next theorem is something called the transitive property of parallel lines. And it works like the transitive property of congruence does. We're transferring congruence then, right? So as a very fast example here, if I know angle 1 is congruent to angle 2, and then angle 2 is congruent to angle 3, then I know that angle 1 is congruent to angle 3, and that's by the transitive property, right? We're transferring the congruence through angle 2. Same thing for parallel lines, right? If line P is parallel to line Q, and line Q is parallel to line R, then we can transfer parallelousness. I don't know the word, but we can transfer the idea of the lines being parallel through Q and say that P and R are parallel. And really, it works for as many lines as you want it to work for. So, for an example, the flag of the U.S., right, has 13 alternating red and white stripes, right, for the 13 original colonies. We know that. Each stripe is parallel to the stripe immediately below it. Explain why the top stripe here is parallel to the bottom stripe, right? Well, the transitive property of parallelness, the transitive property of parallel lines, kind of walks the parallelness all the way down the flag, right? So stripe 1 is going to be parallel to stripe 2. We just said that. One stripe is automatically parallel to the one below it. Stripe 2 is parallel to stripe 3. Stripe 3 is parallel to stripe 4, and we can keep going all the way down. All these stripes are parallel to each other. So eventually, we'll know that the first stripe and the last stripe are parallel to each other. And that's because of the transitive property of parallel lines. Okay? Another useful theorem that we'll find a use for some other time. Okay? Now, like I said before, we're going to get into some algebra, talk a little bit about slopes of lines, right? We have to remind ourselves, and this should all just be quick review, right? The slope of a non-vertical line, and we'll talk about why non-vertical in a second, is the ratio of the vertical change to the horizontal change. Remember that slope is a fraction. That's what a ratio is. It's a fraction that compares a couple of different measures. Okay? The slope is a ratio, so it's a fraction. And it compares the rise to the run. The vertical change, which is the rise, and remember that in the xy axis, in the coordinate plane, y is your vertical axis. So the rise is your change in y, where the run is your change in x, right? But the slope is a ratio of those two changes, right? And we remind you of the slope formula here. Subtract the y's, subtract the x's, and make that your ratio. Now do make sure that it matters here. We mentioned before that the slope, the midpoint formula and the distance formula both didn't matter what order your x's and y's are in. The slope, it does very much matter which order you put your x's and y's in. Only to the extent that you want to make sure they go the same way, right? So if I'm going to compare the y's from this dot then to this dot, then I have to compare the x's the same way, okay? Or vice versa, right? Some more things about slope. Remember a negative slope? Negative slope means down to the right. The line's going down to the right. Positive slope means the line's going up to the right. A zero slope means the line is horizontal. A zero slope suggests that in your ratio that your change in y, the rise, is 0, and then the change in x is some number. 2, 7, negative 12. It doesn't matter, because anytime you divide 0 by any number, you're just going to get 0. So a zero slope is a horizontal line. Now, why did we say in the definition of slope that it has to be a non-vertical line? That's because if you have a vertical line, then the slope is undefined, right? There is a vertical change. There is a change in y, right? That's your rise. But your run, now there's no change in your run, which means that your run would be 0, and you can't divide by 0. Okay? Some quick review. Now, quickly, find the slopes of line A and line D. Line A is this blue line here, which is probably not blue in your notes. Line D is this red line here, the vertical line, which is probably not red in your notes. But those are the two lines you want to find the slope of. Take a second and give that a shot, and I'll show you what you should have gotten. Okay, did you get -1 or -1 over 1 for the slope for line A and undefined for the slope of line D? Okay, a couple of different ways you can find this when you have the coordinate plane and the points. You can use the slope formula, which is this guy here, y2 minus y1 over x2 minus x1. Now I mentioned before, it doesn't matter which way you go as long as your x's and y's go the same way. So I chose this to be my x2 and y2. That's why you have a 4 in the numerator here and a 6 in the denominator here. I chose this guy as my point number 1, which is why you have a 2 in the numerator here and an 8 in the denominator there. Okay, so you have to go the same way. If I go 4 minus 2 for the y's, then I have to go 6 minus 8 for the x's. And that's where you get your 2 over -2 or -1 over 1. Now, if you choose to look at it as rise over run, which you could do, then pick a point, start with it, doesn't matter which one, start with this one. Then to get to the next point, you have to go down 2 is negative, right 2 is positive, so you get to -2 over 2, which is -1 over 1, or just -1. Okay? Now, red line, line D, it's easier than that. It's vertical. When you have a vertical line, the slope is undefined. Okay? But I've shown you, with the slope formula, you get 4 over 0, can't divide by 0. When you try rise over run, then from this point to this point, you have to go up 4, but you don't run at all. So run is 0. You can't divide by 0. It's an undefined slope. Okay? Now, again, from Algebra 1, parallel lines. Think about parallel lines. In order for two lines to be parallel, they have to run the same way, right? which means that their steepness has to be the same, not their length. Okay? A shorter line can still be, or really a line segment, but a shorter line segment would still be parallel to a longer one, as long as they have the same slope. So that's the deal with slopes of parallel lines. Two lines are parallel if they have the same slope. Perpendicular lines. Do you remember what's true about perpendicular lines? Remember that perpendicular lines form right angles. Their slopes are not the same. Their slopes are opposite reciprocals. Flip it and switch it. Right? They're opposite reciprocals. Quick note here. Any two vertical lines are parallel, and then all horizontal and vertical lines are perpendicular. I think that makes enough sense, but it's worth sort of noting. Okay? Now, which lines are parallel? No, you can't tell by looking. What you can do, though, is go find slopes. Okay? The slope of the blue line, we're going to count rise over run. So from this point, I'm going to go up 1, 2, 3, 4. And I'm going to run 1, so 4 over 1. The red line, the slope, I'm going to start down here again. I'm going to go up 1, 2, 3, 4. And go over 1, so 4 over 1. And then this green line, I'm going to start here. I'm going to go up 1, 2, 3, 4, 5, and over 1. So the slope here is 5 over 1. Which ones are parallel? They're the ones that have the same slope. Okay? Don't forget that if you don't have a graph, but you have the coordinates, then you can use the slope formula. Subtract the y's, subtract the x's. Okay? And you have that a couple slides back. All right? All right. Next example. Line H passes through 3, 0 and 7, 6. Now this says graph the line perpendicular to H that passes through the point 2, 5. Now the line's already drawn, but I want to show you where that comes from. Well, perpendicular. I want to draw a line perpendicular. I know that if a line goes through these 2 points, then a line perpendicular to that line would have to have an opposite reciprocal slope. So the first thing I want to do is find the slope of the blue line. So I'm going to write slope blue. I'm going to subtract the y's. I'm going to go 6 minus 0 over 7 minus 3. So I get 6 over 4, which is 3 over 2. Okay. Now the slope of the red line would have to be the opposite reciprocal of 3 over 2, which is negative 2 over 3. Right? Which means that I could apply the negative to the numerator, which means that the rise would have to be negative. So that means that from the point 2, 5, because we want our red line to go through 2, 5, so from this point right here, we would have to apply a slope of negative 2 over 3. To do that, we would go down 2, right 3, and that would put us right here. And then I would draw a line through those 2 points, and I know that that line would be perpendicular to the blue line H. So find the slope of the blue line first, flip it and switch the sign, and that becomes the slope of our new line. And we can just go to the point we want it to go through, 2, 5, apply that opposite reciprocal slope to make the 2 lines perpendicular. Okay? All right. A skydiver made jumps, next example, with 3 parachutes. The graph shows the height of the skydiver from the time the parachute opened to the time of the landing for each jump. Which statement is true? First, part A, or answer A. The parachute opened at the same height in jumps A and B. Okay, now the graph again says the graph shows the height of the skydiver from the time the parachute opened. That means that at time 0, that's when the parachute opened. Well, here's line A, here's line B. Was the height the same when the parachute opened for jump A and jump B? No. So A's out. The parachute was open, answer choice B says the parachute was open for the same amount of time in jumps B and C. Well, the x-axis would tell you how long someone fell to the ground, how long it took them to get to the ground. Well, jump B, it took them short of 4 seconds. Jump C, it took them a little over 5 seconds. So the chute was not open for the same amount of time. So B's out. The skydiver descended at the same rate in jumps A and B. Now, rate. Rate is a ratio, right? It tells us, in this particular instance, how much the height changed as the time changed. It talks about the change in rise over the, that would be slope. So basically what they're saying in answer choice C is the slopes in A and B are the same. Now, are they? Well, A and B actually intersect right there. So they're not parallel. If their rates were the same, then those two lines would have been parallel. Okay? So that answer choice is out, which leaves us with D, which says that in jump A and jump C, the skydiver descended at the same rate, which means that the slope was the same. Okay? Well, we would have to check that. We would have to find the slope of A, right? Which we would have to do some estimating. Okay? But we could find the two slopes for A and C and discover that the two slopes are exactly the same. So the rate of descension, they are descending at the same rate, and so our answer here is D. Okay? Some more uses of slopes. That's it. Your homework's out in Canvas. Make sure you have that done by next time.